Hello everyone, welcome back to the channel. In the previous video, we have seen how we can develop a simple linear regression model in Python. If you have not yet seen that video, you can find the link of the video in the description or in the I-bar here. So, to improve the model of a simple linear regression to a neural network model, we can use a concept called gradient descent. So what does gradient descent mean? It generally refers to using a mathematical function. We try to reduce the losses in the model which we are developing, and thereby improve the accuracy of the model by bringing back the information to the input loop and then running it again. If we have a simple neural network model, let's say we have an input which is represented as a circle, and these are the hidden nodes or hidden network which will work inside any neural network model, and then this will be our output. So what generally happens is the input is taken into different nodes, the hidden nodes, and each nodes try to develop a relationship like this, and thereby giving us one output at the end, which is this. So in this hidden network, we will have weights and biases. So this is a general representation of a neural network model with an input here, the hidden network, and the output. So what the gradient descent means here is, instead of we can use it in a machine learning model like a neural network or a simple linear regression, where we use the input, we go from input to the training data. So we have the input which has initial weights and biases, and it is training our model to get A from B. So when you do this, you will know the quantity of losses because you know the input and you get the target. So when you subtract these, you can find what is the loss or the error in this case. So what we try to do using gradient descent is, we know the loss, so we bring back the loss here, and then we try to update our biases and weights so that when we get to the next set of values, which is B1, we assume that the loss will reduce, or we try to make the loss less. So we go on going back and so on until the loss is reduced until certain limit, and then we say the model is trained well with our data. So to put it in a general context, if we assume the losses and weights, and let's say if we have our equation like this is how the data is. Initially, the data in our model when we are training, this will be our initial weight, and this, what we are trying to do here is, when we are going through the model, is we are trying to reach a point where the losses are very less. So what do we do is, we go for each step, we use a term called learning rate. So this is the element which helps us to be able to understand the data. I already mentioned about going back and forth every time. So to be able to do this, we will use the concept called learning rate. So this is the element we'll use. So once we come back from our A to B again, once we are coming back, we are using a component of learning rate, saying how much should it move from here to here, or how much it should move so that point starts from here and it reaches here. So this is termed as learning rate, and after every update of the learning rate, the updated weight and bias are obtained. So our goal is at our each learning rate or each loop or echo is that it goes from here to here, updating its data as it goes down the slope, and it finally reaches a point where the training is correctly done and the amount of loss is pretty low. So what we'll do here is, for each loop, as I've mentioned, we'll have our updated weight. Updated weight is achieved by taking the initial weight value, then using the derivative of our losses to our weight. So using the weights, how the weights are changing from here to here, and how the losses are changing from here to here, and the weights are changing from here to here, until we reach this point where our losses are the lowest and the training is done so that it understands the information well. So this is what is the generalized concept of gradient descent, and in this video we are trying to develop a code so that we are able to do all this automatically and get a good result. So let's directly go into the code and see how we can develop this model in Python. So if you remember, this is the code which we have developed previously for a linear regression model, where we were able to develop training and testing and get our results. So we can use the similar concepts of the input data as we have developed here. So if you see here, this is the data we'll be using, data of yesterday and today, to be able to determine tomorrow's discharge. So that's what t minus 1 and t represents, and t plus 1 represents tomorrow. So we'll use these two columns as our input and get the discharge of tomorrow. If you see here, I've already inputted the data with the path, as well as use the similar code what we have used here to be able to extract the data initially, then divide it into training, testing, and validation, and also divide it into training data and testing data based upon its length. So this is a simple input of data up to training and testing. So now let's directly start into developing our gradient descent algorithm, which will be run. We need to develop our data sets of weights and biases because they play the major role in updating our loops and reducing our losses. So the first step is initialize the parameters based upon the predictors. So based on the number of data sets which are using for prediction, you'll import the same number of predictors here, because let's say we are using 1000 days to train the model. So for each day of input, you will have a weight assigned to that data to convert it to the output. So that is what this implies. And I'm saying I want to generate the value of the weights and biases randomly, because in the initial stage, I don't know what value to assign, what is the best value. So I'll randomly generate the weight, which is seen here. So the total number of weights generated will depend upon the predictor, the number of predictor values, and I will generate one set of weights for it. Then I will generate the biases as well, similar to what we have the weights. So the total number of biases and weights will be at the same length of the number of data which I'm using it for training. So this is what is parameter initialization is. So once we know the weights and biases, the next step is that we are able to put this into a forward loop. So if you've seen the figure here, we are using this kind of network, let's say, not fully an artificial neural network, but a general network where I'm using this forward loop moving from A to B to be able to have the weights and biases. So the forward pass is I'm using these weights and biases with my X data. So what I'm simply doing here is I'm saying, see, these are the initial weights which I'm giving, and this is the input data. Just use it to understand, just multiply it and give me an output. Then we'll start from there. So as I've said, parameters are weights and biases, which are just, we are obtaining it from initialized parameters here. I'm naming it as parameters. Then what I'm saying here, what I told you just now, is just take the input, multiply it matrix multiplication with weights, and add the bias. Just give me some prediction. So this will be the very rough first prediction because it's not trying to understand anything. It's not trying to see what the losses are or anything, just randomly generating the result and seeing how it is working. So this is the general forward loop, which will get the prediction. Then we will find out what are the losses between our prediction and our actual result. So what we will do here is we will ask our code to develop the losses and gradients. So firstly, if we are talking about the losses, it is like we are saying we have an actual value and we are predicting something. So just subtract it and give me the mean square error, square of error, and tell me how the losses are. So based on the value of this mean square error here, we will know if the losses is too high or too low. And also this will be an indication as we run our loop in it, it should show that our losses are increasing as we go down, as we saw in the figure here. Next thing is gradient. So if you have seen here while explaining this, we have seen that as we go from one loop to another loop, we are improving our weights and biases. That is done based upon the gradient. So how quickly the gradient changes will help us to reduce loss and improve our weights better. So here what we are doing is we are just subtracting our input data and our predicted data, I mean the actual data and the predicted data, and updating our weights. So this is the function of loss and gradients. And the next step here is in the back propagation, we are updating our model. So if you remember, we have talked about learning rate while explaining. So that determines how quickly our model is trying to reach there, because sometimes if you put a very low or very high learning rate, it will either skip the best point and give us infinity or some wrong result. So if in the backward loop, what we are saying, see, these are the weights I'm giving, which we defined it here. And I also am giving you the X data, which is our input data, and the learning rate, see how fast it should move from one point to another point, and our gradient. What you need to do is go to each value of our weight and update it so that we have the improved value of our weights and biases. When we are trying to improve our parameters based upon the learning rate, we improve it and get the next weight which can be used for training the values. So using this backward loop with inputs from our losses and gradients, we update our parameters for each loop and try to reach the best possible loss which we can. So these are the 4 elements which are the most important in our gradient descent algorithm, and these are the ones which will play a key role while developing a neural network model which also has the similar function. So once we have developed the basic code which was necessary to develop the algorithm, the next step for us to be able to start developing our looping system so that we can run our model. To do so, firstly, let's say this is our main function. So this is the information which we are giving to the model from here, which you have already seen. The next thing which you remember is missing is the learning rate and how many times do I want to loop. So let's say my learning rate is 1 to the e power of -7. So let's say I'm starting off with -7, which is 0.00007 or more 0.7, so that I start from a very low learning rate so that I don't skip the best point. Next thing is our Epochs, which is the number of times which I want the loop to run. Let's say, for example, for now it has 1000. So what we need to do is I need to say for I in range of Epochs, so I want it to go from 0th Epoch to 1000 Epoch, and for each Epoch I want it to go to the prediction and give me the forward loop. So for each run of the model, what I will say is I want you to give me the prediction value, go to the forward loop, take the parameters and the training data and give me a random value, because I need to tell the random. So one thing is we've already determined the parameters. As I mentioned, we need to determine how many weights are to be generated. So we need to say initially what are the parameters which I want. So I'll say initialize parameters. The total number of parameters here is, if you remember, it should be the length of the data which you are giving. So it should be the length of this value. So that's what we are saying, initialize the parameters. Now what it will do is it will go to this line. From here it will go here, because we already did this, go here and give us a prediction. Calculate the loss, then update. That would be the next step. So what we should do here is we need to tell the code, okay, here you are predicting something, but the next thing you need to do is tell me my loss and gradient. So to do so, one thing we need to do here is, because it's in a 2D matrix format, we just reshape our actual data, which is our train X here, into this so that it's in a 2D format. And then we will say go to RMSE gradient and see what is the difference between the actual data and the prediction you are giving, and save it as gradient. And then in the next step, because this is forward pass, here we are finding the loss and gradients. The next step here is going into the backward loop and saying update my parameters based upon the learning rate and the gradient. So to make it better, this here is a forward pass. This here will be loss and gradient. And this here will be a backward pass. So these are the three steps which we are doing here. This line, yeah, this would be our backward pass. And then here we are finding our loss functions. So what is the training loss and so on. So the forward pass gives us prediction, then we find out the losses and gradients, then update it again. So using this for each loop, it runs and runs and runs, as you see, until we reach this green point. To be able to validate if that loop is working well or not, is what we can do is can use this function the same with, but I'm saying validating. We are giving the data something, we are giving the model a data which we have never given it before. So this will be our validation data and say, okay, please just go and see how my validation data is performing and see whether the validation loss is better or not. Because the data is being seen here, it's improving and improving as we go, but we should also be careful that we are not overtraining the data. So what we can do here is we can say, okay, you're doing well in training, so what can you do in validation with some data which you have never seen? So this shows us for each 10 loops, I'm asking it to calculate the validation loss and see whether the loss is decreasing or not. So one thing we can do here is, we can say for each thing we can ask it to print the validation loss as well as the training loss, so that we know like what's happening between the training loss and the validation loss. So if we just do this, or we can just do, we can print it like this instead of doing this, so that we know for each 10 how is the losses improved. So what we did until now, we made a forward pass, training loss, backward pass, and we're checking it based on validation. So if we just run the model now, so if you see here, the losses are pretty high because based on the kind of data I'm using, but our main thing is whether the losses are decreasing or not. So if you see, the training loss started with 63,000 something, 632, 63,000. So as we go down, we can see the losses are going. As we go down, it reached 28,000. So one thing, as I've mentioned about the learning rate, let's say I'm giving a learning rate of e to the power of -2, and if I run it again, so what is happening here is, you see, it's going to man. Initially, the learning rate was so good, started 63, but it reached 1.1 at a certain point. It was increasing as it went on because of the learning rate. What happened might be here that you see the figure here again might have started in the left hand side, but it skipped to the right hand side, like it went down and went up so fast that it is giving us NaN results and infinity value. So that is what one thing we should keep in mind when we are seeing this. So now once we have seen that the validation loss are definitely reducing, although that's not the best loss we could get, the next step we can do here is assuming that at our last value that our result is the best result. Loss is the lowest and we are getting the best result. What we can say is at the last weight and biases, I want to use the last values of the parameters and say the validation and testing. So how can we do that? At the end of our loops, after every Epochs is done, what I'm saying is the final prediction. I'm saying please give me the final values of using the last parameters. Just give me the validation value. Then it will give me, don't need this. Can you just save that? Yeah. So give me the final, for the final loop of my data, it will give me the parameters, and I'm using that parameters to determine the errors of my validation and training. So we can just print it, and let's keep this aside for now, which we'll talk. So we'll use the predictions, and if we run the model now again, what we should get here is, see, this will be the value of our training, because if you see here, I'm printing the training first. So let's, to make it more simple, let's just place this here. Yeah. So I have my actual value of training and I have my predictions. So what am I doing here is calculating the last value of predictions and comparing it with my actual value. The last value of my predictions for validation data with my validation actual value. So using the training and validation value, calculating the errors using the code which we have developed. So this is the error code which we have developed, which is a simple code. I have made a video about it. You can find it in the description, the I bar here. So based on that, we can see the RMSE training was 167. The error was this, but it reduced to 150. The correlation was 0.90, whereas in validation it is 0.85. And we have other sets of error values which we can use. So using this method, we are able to determine the training and validation losses. Another step which is left now is to include the testing data. So what we can do here is we use the same concept of validation. Here we'll say final testing data, and I'll ask it to give the test input and then use the same error codes to test it with its original value and print my test. 3 sets of results, which is my training, testing, and validation. So as you can see here in the training, because we are giving it input and we are asking it to update the data and so on, because we are showing it the data, it is able to give you a good representation of correlation because we are training so on and on. The next time we give the next set of data or information which we are not shown it, to see how is it performing, and we give the remaining data so that the last set of data which we are using it as prediction for tomorrow is our testing data, and we see the accuracy is pretty good and the errors are comparatively higher because of the changes in discharge and so on. But in general, we would expect our validation data should give us a good correlation so that it's not missing the parameters. Another thing you can do is, let's say if I reduce my runs, because these are the 2 parameters which you should always remember to be able to get the best result. So if you see here, our error increased as well as our correlation decreased. So it's not like if you make it into 10,000, you'll have the best result, but you need to find that soft point where the number of iterations are give good information. So if you see here, for 10,000 it's 196 and 0.85, but if we do the same thing for 1,000, it would yield similar results. So you need to find how many loops you want to run, the optimal loops to run. So if you see it's 196 and 0.85 again, it's not like changing so much. So you need to find these two values, which are the most important in a gradient descent algorithm, to be able to give a good model. It will also be used in development of a neural network model in our future videos, but this is the information which we need to learn to be able to develop a good neural network model. So that's it for this video. I hope you have understood the basic concepts of gradient descent algorithm and how is it functioning. If you have understood the concept, please give this video a like, subscribe to the channel, and share it with friends whom you think this information can be useful.